All right, cool. Thanks everyone for coming. The Julia folks, but also Jeremy, thanks for coming, and everyone else who's tuning in. Today we want to talk about FastAI.jl, a bit about the Julia deep learning ecosystem, and answer some questions. Let me just share my screen real quick. Okay, can everyone see my screen?
Yep.
Okay, so before we get into the questions, we'll do some introductions. We actually have a lot of people from the Julia ecosystem here today. We'll talk a bit about the deep learning ecosystem that's already existed, why FastAI.jl was created, give an example of it in use, and then showcase it on a different task. Talk a bit about what's next for FastAI.jl and deep learning in general in Julia, and then we get to the questions. You can find a link to the question and answer site in the chat, and they can upvote questions and ask new questions. Yeah. Kyle, I think you already posted it, right?
Yep, it's in the chat.
All right, cool. Okay, so does everybody just want to introduce themselves? Maybe Chris?
Yeah, hello, I'm Chris Rokakis, applied math instructor in MIT, director of scientific machine learning, or director of modeling and simulation at Julia Computing, and also the maintainer of the scientific machine learning libraries. And I build a bunch of things that are, essentially next generation AD and algorithms that are not differentiable with the current machine learning systems.
Okay. Kyle?
I guess I'm next. Yeah, I'm Kyle. I'm a PhD student at University of Wisconsin-Madison, and I contribute a lot to Flux and some of the other packages here in the ecosystem, and I help lead the ML community team along with Lorenz and Brian Chen.
Hey, I'm Ari. Good to be here. I'm a Flux community member and use Julia at emergex.ai for neurosymbolic learning.
Hey, I'm Julian. I'm a research scientist at MIT's Julia Lab. I am one of the Julia GPU maintainers, specifically working on AMD GPU, and also the Dagger current maintainer.
Hey, I'm Tejo. I am a data scientist at Julia Computing and one of the developers of the FluxML ecosystem.
Yeah, and I'm Lawrence. I'm a student here at the Freie Universität in Berlin, and I'm the main developer of FastAI.jl. I also want to thank Jeremy Howard for coming today. And as you probably all know, he's the developer of FastAI. Well, so thanks for being here. Okay, so before we get into why FastAI.jl was created, I want to give a quick rundown of the ecosystem in for deep learning in Julia that already exists, and maybe the people who are most involved with each topic can give like a really quick description, starting with Flux, which is really the core of the ecosystem. And Daria, do you want to say a few words?
Yeah, absolutely. First of all, thank you for putting this together. And yeah, I wanted to take a couple minutes to sort of introduce Flux.jl, right? And what we've been able to build with it. So Flux is at its core, it's the idea behind Flux is that we want to be a very, very simple but flexible library, which can basically showcase Julia's differentiable programming capabilities. And one way that we're showing it with Flux.jl specifically is through what we consider very traditional deep learning at this point. The FluxML ecosystem comprises of many, many packages, be that for building large scale or different kinds of modeling with all the kinds of layers that we're used to, but also it has as part of it a language-wide AD system called Zygote.jl, and of course there's many other such technologies that we've developed on top of it. What we want to do and we want to showcase with this stack effectively is that even though Julia is a very dynamic and high-level language, we're able to write a very generic system on top of it, make it flexible, AD through much more than just what we consider very solved areas in deep learning engineering from an engineering perspective, but also spread it towards different areas that have not been looked at and only have recently been coming to interest. Something like scientific machine learning, right? So one of the core capabilities of Julia has been that you can write generic code, but also create performant kernels out of it. And one way that we use it in Zygote is that we don't really assume the kinds of code patterns that we're going to see, not just for Flux, but in general. We want to differentiate arbitrary Julia code. So that means that we want to showcase more and more packages taking over differentiability as a first class tenet of what it represents. Therefore, Flux is not just super hackable, super flexible, but it also boasts state-of-the-art performance in many of the domains that it's working in, not just for some very large-scale models, for example, transformers, for example, large-scale reinforcement learning kinds of situations, or just image processing. Because of that, we have an ecosystem which is much more varied. Not only do we have very traditional large models like a ResNet or an Inception or whatever, but we also have this slew of scientific machine learning modeling language as a DSL out there in terms of SciML. So we have universal different neural differential equations, which Chris will speak more about. But more than that, what we've been able to show is that using the compiler, the Julia compiler, as something that we can rely on very heavily, we can think of AD as not just something that we take a pass on so that everyone else sort of builds on top of, but we inject AD into existing packages. So that way, because of Julia's composability, we don't really have to have the same kind of development effort that, for example, a PyTorch needs. A very critical example of that is the Flux CUDA integration is around about 150 lines of code, and with that we get really performant kernels right from cuDNN, getting all the fast kernel choosing and stuff like that as well. But on top of that, we can even switch out our backends completely. For example, if we wanted to use the Torch kernels, we can switch out Flux to use the Torch kernels in the backend at a moment's notice. Not just that, we have things like a completely agnostic array interface, which means that for example, the Julia language, for example, is putting out this thing called libblast trampoline. Flux so far used the blast, which just shipped with Julia. And if we wanted to, switch it out for an MKL or an eigen, typically it means that we have a lot of integration, a lot of glue code that goes into it. But libblast trampoline can basically switch out your blast library at runtime, which basically means that now we can inject Flux with the support for MKL and eigen and so on, absolutely without changing any single line in Flux at all. So that's a very exciting, way of progressing the ecosystem, where you have these cordoned off sections of development, which you have people who are very, very familiar with that space, and letting them express themselves the best. We're able to move the entire ecosystem as a whole, and that way, we'll speak about how we work with Dagger and Dagger Flux.jl and so on. But yeah, that's just a very high level, introduction to how Flux works.
Yeah, thanks, Dario. And really the important thing here to note here is that all of these clusters here work really well with another. And as a result, there's some advantages of the existing like Python ecosystem, which is very large, because everything is written basically in pure Julia, it interacts well with each other, and you don't have like a C++ backend for your GPU kernels, your Torch kernels, and there really is less of a divide between the users, building applications, and the developers who are actually implementing new stuff. And as a result, the ecosystem has gotten really far with like probably 1/100 of the manpower that exists in the Python ecosystem. So there's really less duplicated efforts. For example, PyTorch and TensorFlow, they all implement their own GPU kernels, their own array interfaces or tensors. And so this is really where Julia shines. I'll quickly hand over to Chris to say a few words about SIML and auto differentiation and the kind of advanced things that you can do in Julia that aren't really possible in other frameworks right now.
Yeah, so I just wanted to mention a few things that are going on in the greater ecosystem of Julia. So one of the things is that the next generation of differentiable programming is really incorporating physics and biology and all this kind of knowledge into the way that we're doing machine learning, right? Instead of having it be a wholly different world, what we can do is we can use all this prior information that we have about how science works to be able to make it so that way we can learn with a lot less data, and also make it so that way we're actually discovering scientific mechanism, right? We're not just predicting, what can happen in the future, but we're actually figuring out why it happens by incorporating the scientific models with the process, right? And then on the next slide, and what we can do with this differentiable programming stack is actually have these algorithms integrate with the numerical analysis community to be able to differentiate non-differentiable systems. Right. So here, for example, is a chaotic system. And chaotic dynamical systems show up all over the place, right? In weather models, astrophysics, all these areas. And whenever if you actually try to differentiate these with automatic differentiation, you'll notice that you'll always diverge to infinity. That's actually a property of chaos. But there are these systems that people have created throughout numerical analysis that are able to then renormalize with respect to these infinities and make it able to be handled. And so by creating a differentiable programming system that connects with our physicists and connects with numerical analysis, we can create new types of differentiation, which will be stable for handling, new problems that were incapable of being handled before. In the next slide. And the way that we're pulling this all together as well is through using a glue-AD system. So I'm highlighting one of the recent work in abstract differentiation, which is really this idea of, every single AD system has its own ways of doing optimization. Diffractor is able to optimize machine learning code a lot better than Enzyme, but Enzyme handles mutation and scalarized codes like PDE solvers very well, right? And so instead of saying that there's all of these different machine learning frameworks and pick your poison and now you're stuck with it for life, right? Instead, now what we have is we have a whole system, so that way, with just one line change, you can switch between machine learning backends and really be able to use all the optimizations throughout the whole ecosystem, because these are acting on Julia programming language instead of on a Julia machine learning framework, right? That's the key there, right? That our underlying core systems, everything talks to everything in the language, and so since we build it in that form, we can do this kind of build this kind of world. Next slide. And now, one of the core things is that we can differentiate with respect to the knowledge within numerical algorithms, right? If we can differentiate with respect to what's already there, there's just so much more we can discover. So, if you click forward a few times, click, 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 what you'll see is that the way that a differential equation solver works is that it actually is calculating two values, and then the error between those two values is an error estimate. And so if you're allowing the differential equation solver to be used as part of your algorithm, you don't have to come up with, what is a way to do fifth order automatic differentiation and try to make machine learning discover the error, right? We already have the physical tools for knowing exactly what that error should be. And if we incorporate that into our machine learning, then we'll be able to really accelerate what we can do. So here, for example, was a recent paper at ICML we did where we showed that we can get a 10 times acceleration by making neural ODEs that regularize themselves. So as part of the training process is actually finding essentially the recurrent neural network that has the least number of layers. So it's automatically discovering the number of layers and automatically minimizing that amount. And so that is a very nice step. But I think that the most interesting thing about this process is that it requires differentiating through that animation before. And it is essentially a non-quasi-static code, which means that it is not something that you would disable all JAX optimizations. You'd have to disable torch script, and TensorFlow XLA would not accept it. You'd have to use TensorFlow Eager, which we all know is a lot slower, right? So this is an algorithm that requires new software. And so this leaves an open question. What orders of magnitudes algorithm improvements are we leaving behind just because of our software implementations? And what will a new generation of differentiable programming enable for us? All the links for all those things can be found here, and I'll throw it right back to Lorenz.
All right, thanks, Chris. So we can see that there's already really quite a lot in the ecosystem, especially with regards to advanced differentiation systems, scientific machine learning, very cool applications. And so where does FastAI.jl really come into this? FastAI.jl really tries to build on top of all of that and provide a high-level feature set and high-level APIs that make the whole deep learning ecosystem accessible for beginners, while remaining powerful and hackable at different layers of abstraction, similar to the original FastAI. And it really comes with quite a lot of features. You have a high-level API for defining data pipelines, the different training protocols that you can also find in FastAI, customizable training loops with a two-way callback system, abstractions for loading data sets, efficient computer vision data augmentation, you have visualizations, and then for training, logging, checkpointing, early stopping, everything you would want a learning rate finder. And is built on top, of course, of Flux, but also some packages, some of which were purpose-built for FastAI.jl, but they're all kind of able to stand on their own and useful in their own right. So FastAI.jl tries not to be a framework, but more a library, which is really powerful because libraries tend to compose better.
Which ones of those were purpose-built for FastAI?
Dataloaders.jl, DL pipelines, data augmentation, and Flux training. And next, I'll actually give a rundown of some of the features by following an example of a blog post I wrote a few days ago. So if you've had a look at the documentation of FastAI.jl, this is basically all you need to train an image classification model. And we'll go a little bit into the different steps that are involved here. Really, when you want to train a deep learning model, you need four things. You need the data, which means a data set. You need the data processing pipeline, and you also need iterators over those data. So you want to load the data quickly so you can process it in a training loop. You need a model that can learn a relationship, and you need a loss function optimizer, and of course a training loop. So let's see how FastAI.jl deals with these. The first thing is downloading data sets, similar to FastAI. FastAI.jl has access to all of the data sets in the FastAI dataset collection, which are quite a few, as you can see. And you can download them pretty easily with this one-liner. And let me see. Okay. And this will give you the path and save it to disk. Then we can, we have a data container, is kind of like a PyTorch data set, is an abstraction for a lazy container of some observations. So we can treat an array as one, and we can get elements. And we can also, for example, here we load all the image files in the folder, just download, and then we map the image loading function over to get a data container of images and labels. Here we get the parent name, and then you can see one sample is an image and the label is cats. So very quickly we get a data set that's suitable for image classification. Then the next step is the whole pre-processing and augmentation pipeline. And this can actually be pretty involved to set up from scratch and to have it be composable. And in FastAI.jl, we try to make it simple and have something similar to the data block API of FastAI, with the core difference that it already assumes that you have a data container like a lazy data set defined. And then you can define the input and output blocks. Here you put in an image, of course, and want to classify it as a cat or a dog. We can check that the data corresponds to the meaning we assign to it, and then we can define the different steps of the data processing. This here resizes, crops, and augments the images. We apply some pre-processing like the normalization, and then the one-hot encoding to the classes, and each of these steps will only apply to the blocks where it makes sense. So we don't have to write that. And we can put these together, the blocks and the encodings, in a learning method. And this really encapsulates the whole data pipeline. Just from this definition, we can print this whole table that shows us, what representations our data goes through. So we start with an image and a label, and the image is changed, but still an image. Then it's an image tensor that's normalized, and the label is turned into one-hot tensor. So that really makes sense. Of course, the model needs to then map a image tensor to a one-hot tensor, one-hot vector. And yeah, so this encapsulates the whole data processing pipeline. And then it's really easy to create complete data loaders from this. So all we need is to put it together with our data set that we had earlier, and put the method, and then we get data iterators here. You can see how many batches and size, and then we can iterate over those in the training loop. And we also get for free the visualizations of our samples, since we know we specified basically the blocks. We know that it's an image and a label, so FastAI.jl knows how to visualize them. Okay, so this is the raw data, and then we can also check the encoded data, and this is after the pre-processing and cropping. Same as in FastAI, it'll make sure that the images are returned back into like a viewable state, so you can make sense of it. And we can check that the augmentation and everything works out well. Yeah. Then the next part is a model. And here again, FastAI.jl has some backbone models defined for computer vision. And again, in the same vein, we make use of the block information that we defined for automatically creating a task-specific model. So here we basically have a classification head stacked on top, because we know that the output is a one-hot tensor, and we have two classes. So this is this last layer here, two outputs. Very nice. This will give us the probability distribution. And likewise, we can get the loss function for free. We know how to compare to one-hot tensors. That's categorical cross entropy. And can take any optimizers. These are just from Flux. So Flux in this sense similar to PyTorch, giving us the optimizers and also the layers that the model is constructed from. And then we put these together in a learner, similar to FastAI's learner, add any callbacks that we want to add. I think there's quite a few callbacks that you can use, various things. Here we just used to GPU, so that everything happens on the GPU, and track some additional tricks. You only need to call fit one cycle, fine tune, or LR find, which I haven't in this blog post, but you can look at the documentation and you'll see the learning rate finder and the training output. Yeah, and that's basically the basic workflow that FastAI.jl enables. And now I want to hand over to Kyle, who's going to give a short demo of variational autoencoders. So really like a non-standard supervised training loop.
All right. Yeah, so I think the thing we wanted to try and show off with this demonstration is how the existing frameworks that we've built for FastAI can easily be extended to a unconventional training setup with minimal overhead or boilerplate. And so the problem we're going to try to work with here is a variational autoencoder. Here's a quick pictorial representation if you haven't heard of this before. But we're basically taking in some input image X and we encode it into some latent space. And we do that with this distribution, and we'll sample from that distribution, and a decoder will recreate that sample, take that sample and recreate it into the original input. And so in here we have an unsupervised learning scheme because there's only the inputs and no labels at all. But if we look at how we load the data, the stuff where you get the data set is the exact same. And then for our learning method, we use the same block method that Lorenz showed before, except for we just don't specify a label or any encoding for the labels. And it just works. So next, we're going to define a custom model since we're using a VAE over here, which is not a pre-built model you can get off the shelf. And so here we just use a regular Flux model. Anywhere in FastAI you want to use your own model, you can. It just works. You don't have to do anything special for it. And if you scroll down a little bit below, we also define here a custom loss function and also a function that helps us sample from that latent space, like I mentioned. And again, these pieces, the model and the loss, will just plug right into the existing FastAI framework. And we'll see that down below if we look at the learner. So here, when we define the learner, we pass in our encoder and decoder as the model. We choose a standard optimizer that's built into Flux.jl, same data iterator as before. And we plug that all into the learner constructor. And there's absolutely nothing different about this compared to when we were doing a supervised training tasks with image classification. Then I think right under custom training loop, there's a line that's hidden there. But
let me see.
If you double click.
Oh, right.
There we go. Yeah. So what I'm trying to show here is now how you would go about doing a custom training loop in FastAI. So all you have to do is define your own training phase. And here you can see we defined a VAE training phase. And then down below, we define this one function, fluxtraining.step. And we're taking advantage of multiple dispatch here in Julia. Each type of training phase can define its own step function. And the correct one will get called when we actually run the training script. And so just extending this one function is all we need to do. You can see here, if we look inside the function, that it's not necessarily a standard X goes into model, loss of the output and the prediction. We have like a couple different steps, getting the parameters of the distribution, sampling it, passing it through the decoder, and all of that can be written right in there without any extra overhead than you might previously have had. And if you scroll down.
Yeah, and it'll also be compatible with all the callbacks that already exist, most of them anyway. which you can see by the events here. Yeah.
Right. So this one function is all you really need to define, and you get all the full functionality that you would have gotten from FastAI if you were doing something very standard like image classification. So if you scroll down, so here we trained it for just a few epochs. Just for this demo, we didn't go for a long time, but you can see that printout of the table is a standard callback that's in FastAI. I didn't have to do anything special to get that other than define that step function. And now after the training, you can see the a row of digits here. Those are the original digits from the MNIST data set on the top row. And then on the bottom row is the reconstructed digits. For the most part, they look reasonably okay. Here we only trained it again for a few epochs, but if we train for a bunch more, then we'd get a much better reconstruction. But yeah, I think that's it for this demo. Hopefully it gave you an idea of how easy it is to add a new training loop or a new learning method to FastAI.
Very cool. Thanks, Kyle. Okay. Now, I just want to give a, this was the showcase. I want to give some quick notes on what's next for FastAI.jl and the flexible deep learning ecosystem in Julia. There's currently some work being done on multi-GPU training with Dagger Flux. Darian can maybe say some more about that later, or if you have a question about it, we'll get to that in a bit. And he'll also be working on getting mixed precision training up and running. And for FastAI.jl specifically, we want to support more applications like Tabular and NLP. We actually currently have a Google Summer of Code student working on the tabular stuff already. And then some other ideas that are being worked on are a profiler for the training loop based on the callback system, which would really allow to find any bottlenecks and overhead that can be removed and make everything even faster. And then benchmarking the performance of the models against FastAI to make sure that we're using all the best practices and have decent default hyperparameters. And then we also want to add even better support for non-standard learning paths, like the one Kyle was just showing. Okay, and with this, we'll go to the questions. Let me see, I'll pull it up. And the panel. Okay, I think we'll just go straight from the top. The first one, will the future FastAI course be taught using Julia? As far as I'm aware, the official FastAI course will continue being taught in Python. And teaching a course based on FastAI.jl is really more question of time constraints of the community. I might be teaching, co-teaching in the next semester a course on computer vision in Julia at my university, and that would also parts of those would use FastAI.jl, but it's not quite sure yet. I think that's all I can say about that. And then the next one, I need some help for. What are the major shortcomings on technical aspects of Julia that need to be improved before it can become a useful replacement for Python for deep learning related tasks? I think that for the most part, there aren't really any major shortcomings. The biggest thing I've heard is that the GPU compiler of Julia currently uses sometimes more memory than PyTorch, but in terms of speed, it's really on par. But maybe someone, Julian, can give a little bit more detail. or someone, or Daria maybe. You guys there?
Oh, let me hand out the unmute privileges.
Hey, so I did comment on this in the Q&A, but one area that we have issues with deep learning and various kinds of machine learning with Flux is with respect to Julia's GC and ensuring that we don't keep too much GPU memory around. There's a few different ways to tackle this, but we already have one solution in progress being prototyped, which is to essentially use the compiler to determine when memory can be freed and finalized early, such as GPU arrays. So that's a work in progress that is probably going to be coming to Julia reasonably soon.
Okay, cool. That sounds very promising. Then let's get to the next question. Of course, if you have any follow-up questions, you can always butt in. Otherwise, I'll get to the next one. What was a task that was awkward or difficult to code in Python that became easier in Julia because of the language's features? My personal example for this, I'm assuming this is relates to FastAI in Python, is those kinds of non-standard learning tasks that aren't just supervised input and output. And I think the training loop demo that Kyle just showed, how easy it is to create a new completely custom training loop, makes that a little bit easier. Other than that, I've had in Python some problems with very expensive data processing pipelines that really just would slow down the whole training. And in Julia, it's quite easy to write that kind of fast CPU code.
Could I also share a personal experience of mine from developing Flux?
Of course, yeah.
Yep. Let me share my screen. Cool. So let's just go here. Right. So one of the things that we saw about how to reason about Julia's workflows, right? And one of the things that makes Flux very different is that when I started programming with a PyTorch or a TensorFlow a few years ago, it was pretty difficult for me to start with customizing my training loops and learners and loss functions and so on, especially being new to the field, right? But in Fluxland, we really want to be very agnostic to the kinds of backends that people use. So for example, this is how we would define an MSE loss in PyTorch versus how we would do it in Flux. So you would notice that we have a very black box version of mean that's being used versus completely generic one that is provided to us by the language. So whatever array types that you want, we can just push them through and get reasonable results out. Not just that. So this is the practical part of differentiable programming to me as well. Is that this is how PyTorch defines its linear layer. So you would see that there's a bunch of very specific details that one needs to know in order to actually write a very simple layer, right? So everything from how do you handle torch functions to registering parameters and so on. Whereas the exact same version in Flux kind of looks like this. So you have wx plus p and an activation function, which is broadcasted over this whole thing. And that's very close to how the maths actually looks like in the world. And if you notice in the Torch version, you have something that talks roughly the same thing about here in the functional layer, right? But in Julia, all of that can be had in one place. because Julia is going to compile the most optimal code for the inputs that it gets, any method gets. So one way that it actually makes it easier is that even standard tasks, which may not, you might not think are way too difficult, but for someone who wants to quickly iterate, Julia does make it significantly more simple, as you can see here. Back to you, Lorenz.
Thanks for the example.
Can I just
I
add
just
one?
wanted to point out that some of these examples are compared to raw PyTorch, not FastAI. FastAI, inspired by Julia, supports type dispatch. And so quite a few of the things that are limitations of plain PyTorch are not necessarily limitations of FastAI. I will say, though, that I've been wanting for a long time to find a better way to abstract out our training loop, and this idea of using type dispatch looks really interesting, and we should probably look at maybe collaborating and stealing that for the next version of FastAI, because it looks a lot better than the way we're doing it.
Yeah, definitely. Cool. All right, then. The next question is from Logan. What can the Julia community learn from the success of FastAI in general, and any tips for growing and maintaining a positive direction? Actually, maybe Jeremy, you can say a few words.
Sure, I'd be happy to.
Approach of FastAI and how it's helped.
So first of all, I just want to say thanks so much for this great work and for inviting me to be here as well. It's really exciting to see this progress. Probably not a lot of you know this, but I've been messing around with Julia on and off since 2012 when it first came out. And I've always felt like it had the potential to become the main language of data science, and I still feel that way. I think that to get there, there's a lot of things, to be clear, that Python and everybody else can learn from Julia, but I do also think there are things that Julia can learn from, for example, FastAI's success, and are some of the reasons that it's not the main language of data science so far, and it's all about the out-of-the-box experience for people to kind of get going straight away. So there's often been this view that there's a compromise between being friendly to new users and kind of hackability, and that just shouldn't be the case at all. By using a layered API, you can have both. And the out-of-the-box experience for Julia for regular people just has never been as good as it needs to be, in my opinion. Whereas if you look at the out-of-the-box experience of FastAI in particular, it's super clean. You know, you've kind of got the famous 4 lines of code and away you go. And it's kind of like very easy to then start to gradually dive deeper and deeper. So rather than starting with a deep dive of like, look at all the clever things you can do, it's like, well, let's start by getting started and then gradually get deeper into each. So, you know, things like the fact that in those 4 lines of code in FastAI is always the untar data function, which today I just released a new library making that basic capability available to anybody who wants to use it. And the idea that there's a standard way to download data sets, a standard way and place to extract them, a standard way to get access to that, a standard way to checksum those, you know, that everybody can use. And so for the user, it's just 1 line of code. You don't have to think about any of those things. The fact that for any model, you just type 1 method, which is show results, and you can see, you know, whether it's multi-label or whether it's segmentation or whether it's text or whether it's collaborative filtering, it shows you the right thing. And, you know, by the way we do that is with type dispatch, right? And so like we created our own type dispatch mechanism for Python for a number of reasons, but one of them was that, you know, the way you show results depends on the type of the input and the type of the output, right? So if the input is an image and the output is a segmentation mask, then show results should show one overlaid on top of the other with some alpha transparency, you know. And again, it's like all stuff that developers could figure out how to do eventually, but by making it easy in that out-of-the-box experience to kind of get started, it's in my opinion, that's how you kind of get the mind share. And it does mean then as people become more of an expert in your platform, they can do more and more of the manual stuff, but they don't have to until they get to the point where they need to. So yeah, in my opinion, Julia's type dispatch functionality, which is way better than what we created in FastAI and always will be because it's a native part of the language, makes it dead easy, you know, for you to do the right thing for users for whatever their data type is and so forth. And it does mean you need to make sure that you use typed tensors, right? So we actually invented typed tensors for PyTorch. So previously they were like float tensors or half precision tensors or whatever, whereas we said, okay, this is an image tensor or a black and white image tensor or a segmentation mask tensor or a bounding box tensor. And so with that combined with type dispatch, even in the restricted ability we have in Python, we were able to say, okay, guys, this is, you just type this command, whatever you're doing, and it's going to give you some sensible results. And so then that meant that for our tutorials, we could focus on the model building, the data processing, the data cleaning, the error analysis, like focus on the challenging enough kind of question of like, how do you do deep learning and make it work properly, rather than having to say like, okay, well, these 10 lines of code are needed to loop through your batch and collect your input and output tensors and plot them with these axes and blah, blah, blah. So, you know, I think you're in a great position with this library, and my suggestion would be to leverage that. And then in Julia more generally, I think hopefully this is the direction it's going, things like time to first plot and, you know, memory overhead and all this kind of thing will, you know, there'll be some way that I can just type Julia, or maybe there's some slightly different command like mini Julia or something, and I'll get something that takes 500K of memory and starts up in 0.1 seconds, and I could, you know, use conveniently. So yeah, that would be my opinion.
Cool. Definitely some good advice. And this simple interface really also go of FastAI.jl and using multiple dispatch for that is really the main idea behind the interfaces, but the execution and having it work well together with everything you could throw at it, including once you have different high-level applications, that's definitely still needs some work. Yeah.
And by the way, the other cool thing about that is that it's becomes much more easy to create a no-code front end. You know, if you want to create a GUI on top of something that has typed tensors and generic functions, then that maps to a GUI very nicely.
I mean, the block method I showed that's basically the kind of the type annotation for the data, and there are plot recipes defined for the different blocks. So it is really just a one-liner, and I don't know if I didn't go into the short version of the example. Let me just share my screen again real quick. Hope you can see it. But so here, of course, this is the same as untar data. Then this is one line on multiple lines for loading a data set. Here we annotate the data with the different types, and then this one basically does most of the things that we pulled apart below, where it selects the right loss function, knows how to put the head on the backbone, and then the visualizations these are also dispatching on the blocks. And yeah, probably this one you don't need if you have a data set. You could make it much simpler. But the basic idea, I think, is there. All right, cool. Then I'll get to the next question. Let me just find the panel again. Okay, this one's answered. This one too. Next question with 3 words. Do you think that Flux.jl is good enough to replace TensorFlow, PyTorch, JAX as a daily driver for deep learning projects? And I'm assuming this means now. For me personally, I would say yes, if you're not reliant on the huge multi-GPU setups, which is still in the works, but the ecosystem is pretty robust by now. Again, performance-wise, it's really just the slightly higher memory allocations on the GPU. But for me personally, I'm using it as my daily driver, and there are companies that are using it, like NVIDIA, in production. So I think it's really coming to a point.
How about TPUs and the new TPU VMs?
I'm not very qualified to answer that.
Daria, maybe insight.
Daria, do you know what the status is?
So we used to have a completely functional TPU setup with TPU.jl. We actually did work a little bit with the Google team on getting Julia on TPUs. So as for the new VM is concerned, there's active development going on with some of the GPU maintainers, Tempest and Keno, or looking into hooking into the TPU VMs directly. There's a completely new API that TPU v2v3, the latest one has put out, right? And we're going to be hearing much more about it very soon.
Also, that's going to take advantage of the new pluggable compiler infrastructure, right?
Yeah, that's right. So we have a lot more flexibility now with the kind of API that they're releasing. So we're able to use much more of Julia directly rather than having to call into their APIs a lot more.
All right, cool. Then on to the next question. Do you plan to translate the Fastbook material to FastAI.jl? This has come up multiple times actually, with people asking, and I think for one, we need to clear the copyright with Jeremy here. But I think porting the complete book right now, I'm not sure if that's if the manpower is there, since unfortunately none of us have the ability to work in FastAI.jl full time. But I would love to have the opportunity sometime, maybe when I have more time. Yeah.
I mean, maybe that could be some kind of community contribution thing. I mean, we don't have permission ourselves from O'Reilly, but like porting the code would obviously be fine. And then you can just say like, okay, here's a Julia version of each bit from the book and not actually copy the prose.
Yeah, I mean, I think taking the book as inspiration, create helpful tutorials, and to see, how can we get the same simplicity that there is in the APIs of FastAI and FastAI.jl. It's definitely already been an inspiration. Yeah. All right. And then the last question on the Q&A side is, what are the best Julia learning resources for Python users? And one comment. Let me see. Okay, Brian, do you want to say something about that? Since you wrote a comment, just share it. Brian's still there. Does he have unmute privileges, Kyle?
I think he should.
And he's here.
Okay, I think it should work now. So basically what I posted here, there is a set of a couple of notebooks that you can look at if you want a direct translation in a crash course. Julia Academy is really the best introductory source because it has tutorials on the language as well as on higher level libraries. And you may want to look at also possibly some of the workshops at JuliaCon, which just happened, which I didn't list on here. If you want to look about machine learning and Flex specifically, the Flex tutorials are kept up to date. And there's one which is literally a port of one of PyTorch's intro tutorials. So you can put that side to side and compare between the two. And also, I believe either the Flex homepage or the GitHub repo links to all the community forums that we hang out on. So if you can't decide and you're looking for something specific, feel free to hop on there and we can help you out there as well.
All right, thanks, Brian. And that was actually the last question on our Q&A side. Of course, if there are any more, we can answer them right now. So just give you some time to think.
I got to run. Thanks, everybody. It's been very interesting.
All right. Thanks for coming, Jeremy. It was nice having you. And if there aren't any more questions, then we're actually right on time. So thanks everyone for coming and tuning in. And yeah. Sorry?
There's still more questions on Pigeonhole, apparently.
Yeah. I think this one would have been one probably for Jeremy. Because it was about Swift. But maybe we can skip to the next one. Will FastAI create recipes for running the MLPerf benchmarks?
I haven't really looked at the MLPerf benchmarks. I guess it can be done, though first I would like to benchmark against FastAI to see that we're using all the same tricks and getting good performance out of the box.
Yeah, we've talked about benchmarks before, not specifically for FastAI, but for Flex in general, MLPerf being one of them. One of the challenges for MLPerf is that it's all about how much you can scale horizontally and vertically. And for that, we need good distributed support. And we also need the same level of like vision and NLP model support with that distributed functionality that other libraries have. We have pretty good vision model. We have relatively comprehensive vision model and NLP model architecture coverage with transformers.jl and Metalhead, but we just don't have the distributed stuff just yet, and those pieces aren't put together yet. So I commented on there, but basically we are trying to set up benchmarks for Flex in general. And then once those are up and we have kind of like a speedometer dashboard, then we'll start thinking about more specific ones like MLPerf or even DawnBench.
Yeah, and just to jump on that and answer the next question, which is about finding benchmarks, comparing Flux to non-Julia packages. Daria has been working on FluxBench, which will be public once it's ready. It'll be how we benchmark the library as maintainers, and the results will also be publicly available on a dashboard for people to look at.
Also, we do have DDP and data distributor as well as model parallel training that's going to come up really soon as well.
Then there was a question about using GPUs for augmentation in environments like Colab where there aren't as many CPUs available. It's not currently implemented, but there is the architecture was designed in a way that it will be possible. I could probably open an issue for that, and then you can follow that for any progress made on that. Yeah. Okay, that's that one. I have the benchmarks.
Yeah, then the next one is how do the other deep learning packages like KNet and Avalon fit into the ecosystem? I guess for KNet, they use the same underlying kernels for things like convolutions. They use NNlib, which is what backs everything in Flux. Of course, the high-level API is different. Same thing for Avalon, and they also have, maybe different goals. So I think in Avalon they use a different AD system than the one that's used by default in Flux. But
also, like many of the packages that were written now for FastAI.jl should also work with other deep learning frameworks, and even Flex training probably you can make work with KNet and Avalon. I've also actually thought about just writing a wrapper for PyTorch so that you can use it in Flux training .jl and FastAI.jl while still having like fast Julia data preprocessing and everything else the ecosystem has to offer. So in that sense, the ecosystem and the libraries are really composable, and you can use them well together. Okay. Now, okay, just I think that's all. Let me just refresh the page. Check the chat. Okay, this time I didn't miss any, right?
No, I think we're good.
All right, cool. We're having, I mean, this call is usually the ML ecosystem coordination call, which happens every 2 weeks. So if you're interested in following along with the developments that are happening, tune in 2 weeks. Usually, though, this call is at a different time, which I think it's 6 p.m. European Standard Summertime.
Yeah, it's on every Tuesday at 12 p.m. Eastern time in the US. And you can find the links and all the calendar posts all on the Julia Lang website.
Just share a link. There's a calendar with all the links. So yeah, we would love to see you at one of the next meetings. And if there aren't any more questions, then thanks everyone for coming, tuning in, and see you next time.
Thanks, everyone. Bye.
Thanks.
Bye.